So welcome everybody. Thank you for once again joining our weekly seminar. It is a distinct pleasure to have with us today Dr. Susmita Adhikari, who is actually a graduate of my own alma mater, the University of Illinois, the Great Plains of the United States. And actually, there are several of us, Susmita, here in this department and the Institute of Astrophysics, who have graduated from the U of I. So there's me, there's Kostas Stasis, there's Nikki Kilafis, who I see on the participants list. Friends, Susmita is the kind of graduate that increases the worth of our own degrees by celebrating the name of the great U of I. So she did her PhD at the U of I with Neil Dalal, and then she moved to Stanford as a Kaipak fellow. And she was at Stanford at the same time as our own Yannis Liodakis, so the connections continue. And now she's at the University of Chicago, another institution with close collaborating ties with us. So we're very happy to have her with us here today. She's going to tell us all about the structure and evolution of dark matter halos. So without further ado, Susmita, the floor is yours.
Thank you so much, Vaso, and thanks for the invitation. And it's a great opportunity for me to speak at the Fourth Institute in Crete. Yeah, and it's been, lovely making connections there as well. So thanks. So if everyone can see my slide and hear me properly, I think I'll go ahead. I'll be talking about some work that I've been doing recently on understanding the outskirts of dark matter halos, in particular the splashback radius, and telling you about some recent developments both on the theory and the observational side. So this is work that I've done with many collaborators, many whose names I've jotted down. All right. So to start at the beginning, we know that most of the energy in our universe is made of dark matter, and a lot of this dark matter actually lives in gravitationally collapsed structures called dark matter halos. So dark matter halos are essentially endpoints of structure formation. These are bound virialized structures. These are thought to be bound virialized structures and are basically some of the regions in the universe with the highest densities of dark matter. And of course, these halos are basically the structures that harbor the stars, galaxies, quasars, and all the beautiful, interesting things that we can see out there in the sky. They grow out, so these halos, they grow out of density perturbations in the matter field in the early universe that grow gravitationally to collapse and form objects called halos. And halos, apart from the rest of the cosmic structure in the universe, what distinguishes them is they are basically things that have collapsed in all three directions, and the evolution of things inside of them is sort of independent of the overall background evolution of the universe. So going back, as I was saying, these are the densest regions of matter density in the universe. They are the centers in which galaxies form. And dark matter halos are basically, they grow higher, at least in the cold dark matter scenario. We think that the smallest structures form first and grow to form larger and larger objects. And the smallest dark matter halos are essentially what harbor these faint dwarf galaxies, and the largest ones can even harbor many of these coalesced smaller structures and form what are known as galaxy groups or massive galaxy clusters that are bound together by an overall potential well. So I just like to keep this picture at the back of our mind, that our dark matter halos are essentially composed of diffuse dark matter particles, but also the most massive ones that we see are also formed of smaller coalesced structures that have merged hierarchically to form these massive gravitationally bound clusters, for example. So a lot of my work has been to understand the internal structure of these dark matter halos. And one of the questions that I've been engaged in answering is over the last few years is understanding the boundaries of these dark matter halos. So just stepping back, over in general, when we think of the dark matter halo and what its boundaries are, where its edges are, how far out does the gravitational influence or the gravitation, is there a specific boundary that we can define? And depending on who you talk to, people can define a variety of boundaries which can be relevant to their work, essentially. In general, it is defined as the region of the universe that contains some factor times the background uniform matter density of the universe, like an R200 or an R virial, etc. Right. So on the right, on the left is just a picture from a dark matter halo simulation, and you can see on the right is the density profile. So density on the x-axis going out from the center of the halo to the outskirts, and depending on who you talk to, you can define a variety of radius, which can in fact be spanning several different physical regions inside the halo. However, one of the things that we have now come to realize is that, in fact, if there is, while traditionally we have defined the halo boundary as with respect to some reference uniform density, but there is in fact a more dynamical definition of the halo boundary that we can come up with. And one of the ways of looking, and one of the intuitive ways of sort of looking at this boundary essentially can be gained from looking at the phase space of dark matter halos. So if we look at a dark matter halo and if we look at its evolution through time, and instead of looking at it in real space, if we look at the phase space which is shown over here, sorry, the y-axis is missing. So on the y-axis over here is the radial velocity of particles, dark matter particles. So it is a velocity with respect to the center of the halo. And on the x-axis is basically the distance from the center of the halo. So if we look at the region around dark matter halo in phase space, we can see that in phase space, actually, you can distinctly distinguish different regions of the dark matter halo. So if you're in a region far away from the center of the halo at large R, you're essentially in this region where you're expanding away, where you have a positive radial velocity, so you're moving away from the halo. So particles in this region are essentially moving away from the dark matter halo. As you move closer and closer to the dark matter halo, you essentially reach a region where dark matter particles are cutting off from the Hubble flow and are starting to fall into the gravitational potential of the overdensity inside. So as you move to smaller and smaller radius, you reach a region of particles that have more and more negative radial velocity. So this is the region where they're falling into the halo. Until a shell of dark matter particles would reach the center of the halo, it would just cross over smoothly and have a positive radial velocity now, so just moving in the other direction. But in its orbit, eventually, it will, as it moves further and further out from the center, the potential, its velocity drops because it's slowed down by the halo potential. And eventually, because it's orbiting, it will turn around, or essentially what is called splashback into the halo, right? So this is this most recently accreted stream of matter, essentially, which traces the orbit of particles. And the most recent and the first apocenter, essentially, of the orbit of the most recently accreted matter, essentially separates out the multi-streaming region of the halo, where things are in orbit, from the outskirts infalling region of the halo. And that essentially forms and that can be thought of, so the shell that is made of the most recently accreted matter at its first apocenter is essentially can be thought of the region that bounds the orbiting region of the dark matter halo. In general, if you look at, so the density profile of the dark matter halo is essentially just the integral of the phase space, where you go to every point in space and just count up the number of streams you have at that location. So it's just the integral of the phase space in the radial velocity direction. And in an idealized simulation, you would actually, at each of these turnarounds, because it's at its apocenter and the particle is spending just an extra amount of time there because the radial velocity is 0, in an idealized smooth simulation, you actually get caustics at each of the apocenter. And in fact, at the furthermost, outermost apocenter, you get a very strong caustic. In fact, in realistic halos, where halos accretion is not spherical or smooth, you actually begin to wash out this dark matter caustic feature. And eventually you don't see as many caustics inside the halo. But despite that, at the edge of the halo, you do see a sharp rise in the density from when you move from the outskirts of the halo to the inner regions of the halo. So essentially, one can think of the dark matter halo region to be divided quite neatly into a few regions, where you have the orbiting multi-streaming region and the infall region, which is basically separated out by the shell where the particles are very close to their apocenters. And of course, far further away, you don't have things which are falling into the halo. Right. This was actually, the reason we all started thinking about this essentially was earlier sometime in 2014, Benedict Deemer and Andre, they were looking at simulations of dark matter halo, and they saw that near the edge of the dark matter halo, the density profile actually deviates significantly from the usual way that we think of dark matter halo profiles. So on the top panel here is a plot from is the average density profile of our halos and simulations, and in the bottom panel is a logarithmic slope of the density profile. In general, we think of halos having an NFW-like profile where the slope is -1, where the rate of change of the density profile or the slope is -1 in the inner regions, and it asymptotes to -3 in the outskirts. But what they found is that in a narrow localized region in the outskirts of the cluster, the slope actually can deviate significantly from what is expected from NFW, which is shown by this dashed line here. In fact, the slope can be really steep. So there's a very steep fall off in the density near the outskirts of the dark matter halo. So in a follow-up work of that paper, we essentially showed that this boundary, this location of the minimum of the slope, essentially where the density slope becomes really narrow, essentially corresponds to this to the phase space boundary of dark matter halos. So while earlier I was showing you idealistic phase space diagrams, this is a phase space of an n-body sample of dark matter halos. So you've washed out a lot of the inner structures, but despite that, you can clearly distinguish, even in an n-body simulation where halos have different shapes, sizes, and histories. You can distinguish the infall region of the halo from the virialized, or the not virialized, but the multi-streaming region of the dark matter halo. And we saw that the slope of the density profile essentially becomes very, very steep at this boundary. And in fact, if you choose on particles that have very low velocities, low radial velocities, essentially to choose particles that are on their first apocenters, you can actually make this feature sharper, showing that it corresponds essentially to where these particles are turning around in their orbits. Right. So this feature has now the location of the minimum of the slope has now is now more colloquially called the splashback radius, but it's essentially thought to trace the boundaries of dark matter halos. Further, we showed that because without going into the details, we could write down a simple model based on spherical collapse of dark matter halos, but starting from very simple assumptions of how the spherical collapse calculation proceeds in a lambda CDM universe. And the only difference is that we had an accreting dark matter halo, in the sense that we had a halo that's potential was growing with time because it was accreting mass. And for these accreting halos, we could write down exactly where the splashback radius should be. So the idea is quite simple. So if you had a constant dark matter potential, every time a particle falls into the halo, it would basically move out to the same radius, or essentially its first turnaround radius, if your potential was not changing. But if your halo is growing with time, which realistic dark matter halos do grow with time because they're accreting more and more mass, at every subsequent orbits, as your halo is growing, your orbits will start to shrink with time, right? So you start off with the first orbit. When you reach the second orbit, your halo has grown. So your first apocenter is essentially smaller than where you first cut off from the potential. So so essentially we showed that the location of this feature, as was found, is it does depend on how quickly your halo is growing, and that is actually its primary dependence, that it depends on the mass accretion rate of the dark matter halo. So a faster growing halo, a halo that is growing quickly with time, will have a smaller splashback radius in units of R over R200M. I'm sorry, I don't know why I've missed some of the labels. So fast accreting halos in units of R over R200M have smaller locations of their splashback radius, whereas slow halos tend to have their boundary extended out, and the first apocenter can be at a larger distance, and therefore their splashback is at a larger distance. We also showed from some simple arguments that the location of the feature in units of R over R200M should also depend on the redshift at which these halos form, essentially because you're at a higher redshift, the expansion rate of the background universe is different, so your relative density at splashback will be different from what you get for a different redshift. So these are basically the primary dependencies. We saw that essentially this feature is a dynamical boundary of the dark matter halo, and it traces the evolutionary history of dark matter halo, and essentially we can trace sort of whether it is a fast accreting halo or a slow accreting halo, or at what phase of evolution the halo is in the universe. So moving on, just like dark matter particles are expected to show this feature in their density profiles, we also expect substructure or subhalos. So the subhalos are basically the as we were talking about it before, these are already collapsed structures that form into larger potential wells. So they also actually, their dynamics essentially traces the potential of the underlying larger dark matter halo, and they also evolve in a very similar way. So most subhalos and the galaxies that they bring with them will also trace the particles' splashback radius, and unless of course they are very massive subhalos that experience other effects like dynamical friction. So essentially, The subhalos and the particles are expected to have very similar dynamics, but because subhalos are extended, they have some extra features like tidal disruption and dynamical friction. So one thing that we found is that the splashback radius can also essentially be a probe for these processes like dynamical friction, because you can see how the location of the feature changes with the mass of the subhalo with respect to its host halo. So why I am stressing on the subhalo part of this is because going ahead, one of the ways that we have been able to actually observe this feature is through its signature on the galaxy distribution in massive cluster mass halos. And essentially, this is because both the galaxies and dark matter particles essentially are expected to splash back at similar locations. So before I go into the next part of the talk, I should also pause for questions, and please feel free to interrupt me if you have questions. I can't see hands, so yeah, do interrupt me as and when you have questions. So just to step back and think why this feature at the edges of halos, why this might actually be interesting, if interesting at all. Of course, we see that the splashback radius is a physical definition, is a dynamical definition of the boundary of the dark matter halo. So processes which are specific to the high velocity dispersion, etc., that comes with the interiors of a halo are essentially very sensitive to where this boundary exactly is. Moreover, it is a probe of the growth history of the halo through time. And I think one of the things that is very important to note is also it's a fundamental length scale inside the halo structure, and it should be present if there is a dark matter halo, essentially. So it is, if there's dark matter around your galaxy, it should have a feature at its boundary which separates these phase-based regions quite neatly, particularly for the most massive objects in the universe. It's also formed by the most recently accreted material onto the halo, so it's not very phase mixed. So its dynamics and the location of the feature can actually be understood by very simple physical arguments. And what we found is that very idealized simple physical arguments can actually do a very good job in explaining the location of the feature, particularly in a wide range of halos and n-body simulations. And of course, it's far out from the central regions of the halos where you have to worry probably less about baryons. And I think the most exciting thing for me has been that it has been accessible observationally, because it's a feature that just stands out in the density profile of dark matter halos, which we have been trying to measure in the astronomy community forever. And it's essentially a feature that is at the edge of that, that comes out when we look at the slope of the density profile. There's been a lot of work to actually not look at this summary sort of slope definition of splashback, but also really understand the exact boundary of the halo by tracking particles to look at what shape these shells make. And we've learned a lot about dark matter halos and how they occupy their spaces. And also, so this is work by Phil Mansfield, Benedict Deemer, who have been looking at these exact shells in dark matter halos. And I think a lot of just understanding the boundary of halos has helped us sort of clarify a lot of different things just by being able to define what belongs to a halo and what does not belong to a halo. One of the things I'm very excited about is also the fact that we can now write down the match with the expected mass functions using these new definitions of halo boundaries is also quite agrees well with the theoretical expectations. Anyway, but moving on, as I was saying, the location of the feature is set by very simple physical principles. So basically, you're solving for gravitational collapse of a cold dark matter halo in an expanding universe. And the splashback radius is essentially where your particles are turning around in its orbit. So some of the theoretical work that we've been doing on this is sort of relaxing different parts of that statement and seeing how the location of the feature is sensitive, for example, to the model of gravity, to the nature of the dark matter particles, or basically the nature of the way the universe is expanding, and if this feature, the location of this feature, is sensitive to these things. So one of the things that I've been working on personally, was understanding if modifying gravity changes the location of this feature, essentially because for these really massive objects, the boundary of the halo is expected to be close to 1 to 2 megaparsec, and that is where a lot of these modified gravity models tend to have their transition regions. So these modified gravity models, just to give a very short review, I'm not an expert on modified gravity, but just giving a short review, is essentially these are these gravity models which say that in regions of on large scales, you have these scalar tensor theories which deviate your theory from the usual GR, but in dense regions you will converge back to general relativity. But on larger scales, you might your gravity theory might look different from GR. And oftentimes in the theory space of some of these models, the transition region between the two regimes can oftentimes lie in the edge of near the edge of the galaxy cluster on a 1 to 2 megaparsec scale. So essentially, your particles, when they're falling into a halo, are coming from a region of enhanced gravity. In the modified gravity regime, the gravitational constant is about 4/3 GR. So your halos, so your particles are falling in from a region that has sort of 4/3 enhanced gravity to the inner regions of the halo, which has your gravitational constant close to G. So one of the things that we did is we tried to calculate the orbits of these particles in these modified gravity models to see how the enhanced gravity in the outer region of dark matter halos changes the dynamics of the particles. So what we found essentially is that because the particles are falling in with an enhanced velocity, and because splashback traces the first sort of orbit of these particles, they can leave their signature on the density profiles at where exactly the location of the splashback is. However, the more stronger effect we found was with respect to small halos falling into a larger dark matter halo, and in particular because the motion of the small halo is very sensitive in particular because of the dynamical friction force, which is proportional to the velocity with which a galaxy falls into the dark matter halo. So the dynamical friction force essentially tends to slow down objects inside of dark matter halos, and things that, and because it depends on the velocity of the particle, and because modified gravity increases the infall velocity of the particle, we saw that the effects of dynamical friction are actually reduced in these modified gravity models. So if you expect in GR the difference between your particle splashback and your particle splashback and your dark matter halo splashback, or your subhalo splashback to be large, the difference between the particle and the subhalo splashback is reduced in F of R gravity-like models. So that was our main result, showing that the location of where galaxies turn around in their orbits is sensitive to the model of gravity that you put in. And in principle, it can lead to a 20% difference in the location of the splashback feature. apart from looking at modified gravity, we also asked some simple questions like what happens if the dark matter particles themselves self-interact. And I won't go into a lot of details of this because I want to also touch into the observational studies that we've been doing. But essentially, the idea is that if you have some amount of scattering in the dark matter particles and a channel for dark matter particles to lose energy or exchange energy with other particles during their orbit through the halo, you might expect to change the location of how far out they go out in their orbits in the first place. In particular, in the as particles reach the inner region of galaxy clusters, in high density regions they can have large scattering and lose energy, and then we could expect to see if that leaves an imprint on their apocenter orbit. What we found, though, was the effects are small, particularly in the sense that instead of making the splashback radius move dramatically, it actually makes it wider because you have just introduced a dispersion in the different locations at which different particles turn around. But we did find that depending on whether or not you have a young or an old halo, particularly because their inner dark matter distributions can be significantly different, we can see differences in self-interacting dark matter models in the location of this outer feature. So for young halos, we found that for different interaction cross sections, we have a similar location, but for old dark matter halos, we found that there can be a spread, there can be a small move, there can be a systematic movement in the location of this feature with increasing accretion rates, with increasing dark matter interaction cross sections. Right, so I'll just pause for a second for questions, if there are any. And if not, I'll move on to the...
I don't see any hands now, so I think we'll ask our questions at the end.
Great. All right. Yeah, so the final things that I'll talk about is essentially observations of the splashback radius. So this was really exciting for me because mostly during my PhD, I worked on simulations and writing down theory. And by the time I was ending sort of grad school and starting my first postdoc, we started to make the first look at this feature actually in observation. And that was like a really satisfying experience for me. So I'd like to mention that. So over the past few years, I've been involved with the Dark Energy Survey in trying to measure and see this feature in realistic, in actual dark matter halos. In particular, we have been focusing on looking at galaxy clusters. So galaxy clusters are the most massive halos in the universe, or are thought to be the most massive halos in the universe, or the most massive collapsed structures in the universe, and they shine in a variety of wavelengths. So a dark matter halo, a dark matter halo of a cluster is around 10 to the 14 or 10 to the 14 or higher dark matter mass, and it appears in the sky as a cluster of galaxies that are bound and are orbiting in the overall potential of the halo. So they are found in different ways in the universe using the gas in these halos are hot and they can shine X-rays. They're found in optical by looking for dense clusters of galaxies in the universe, and also in sort of these CMB surveys, looking for scattering of CMB photons inside of these, in the hot gas of these clusters. So how have we measuring this feature? Essentially, the highest signal to noise measurements have been made using the distribution of galaxies in these clusters. So essentially, we see how the galaxies are distributed as a function of radius, and they're expected to trace the potential of the underlying dark matter halo. And other than that, we've also been studying them using the lensing of background galaxies. So we're looking from here, and if we have a background galaxy and a massive cluster between our line of sight, the distortions of the galaxies in the background due to gravitational lensing teaches us about the potential of the dark matter halo. And we can now really quite precisely map out the matter distribution in these massive objects using these telescopes. The first observations of the splashback radius were actually made quite early using SDSS data. So these were looked at using galaxies in what are known as these red mapper clusters. So red mapper clusters, and red mapper is an algorithm essentially to find clusters in the universe in the optical. So they look essentially for these clusters of galaxies and define sort of the center near the brightest central galaxies. And the density of these galaxies is essentially measured to tell us what the underlying potential of the halo is. So what basically do is look at this projected number density of galaxies as a function of radius. So essentially, going from the center of the halo outwards, we count up the number of galaxies in different radial shells to evaluate projected number density profile, and basically fit our halo model, the Democratic halo model, which has a splashback radius, to that galaxy distribution to find whether or not we see a sharp transition at the boundary. So there were several issues that I will point out, start in those early measurements, and in fact, in general, in the red mapper cluster sample. Going further, we have also been measuring these, extending our sample of galaxy clusters using the DES survey, and also not just selecting optical clusters, but also looking at different selection methods of galaxy clusters, particularly in using the SZ, the Sunyaev-Zeldovich effect, to find galaxy clusters. Right. So in the DES year one, we measured the splashback radius around these, firstly around these optically selected clusters, and the gray band essentially is the measurement using the cluster cross galaxy density, the number density of galaxies around cluster, and measuring their slope. And we saw a significant, there was a significant detection of the slope becoming much steeper than -3. And we found the location of the splashback radius using around these massive clusters that are around 2×10⁻14 in these red mapper observations. Curiously, for these clusters, we found, as in an earlier study with SDSS clusters, that these the splashback radius in the galaxies is shifted to a smaller radius compared to what we expect from simulations of dark matter halos. So if you match the mass distribution of the halos in n-body simulations and compare where the splashback radius should be, there was a 20% offset between the location of splashback radius and the theoretical expectations. This was actually quite consistent with what we find when we look at weak lensing around galaxy clusters. So instead of looking at the galaxy number density distribution, we can look at the lensing of galaxies around the clusters and actually directly measure the dark matter distribution, not infer it from the galaxy distribution. And in the DES-Y1, what we found is that the weak lensing measurement also shows an offset from the theoretical expectation, which is shown by this black line, and the measurement is shown by this pink shaded region. Of course, weak lensing is a much harder measurement, and the error bars, it's not like it's not a very significant measurement, but there was hints for a shift in the outer profiles of the halos of these objects. There were a few other outstanding issues, like particularly with the galaxies, we expected, as I was saying, that massive galaxies, because they experience dynamical friction, should show a shift in their splashback radius. So as you look at brighter and brighter galaxies, you should see a shift in the radius of the splash, shift in the location of the minimum of the slope, which also we did not observe in data, but which is observed in simulations. This was quite, so for a while we were excited and also maybe not excited about it, whether we were seeing some discrepancies from theory, whether it could be some interesting model of dark matter, or more likely an issue of cluster selection. So the red mapper optical clusters are actually, eventually we found, are very prone to biases, selection biases, particularly because it's hard to measure the masses of those clusters accurately. They're usually measured from the number of galaxies that are there that are thought to be associated with that cluster, but there are issues with galaxies projected from the background and also orientation effects. So therefore, one of the things that we try to do is, instead of using these optically selected clusters, we went to a different kind of selection method, which is the galaxy clusters that have been found using their signal in Symonds-Zeldovich effect. So essentially, what this does is you have the microwave background photons traveling through a cluster, and they get scattered by the hot cluster gas. And essentially, what you see is a difference in temperature in that region where there is a galaxy cluster in the sky. So these SZ-selected clusters is a completely independent way of selecting clusters, essentially, and their mass proxy for the mass is also completely different from these optically selected galaxy clusters. And in general, the SZ clusters are thought to have smaller scatter in their mass observable relationship. So recently, we've been driving an effort looking at studying the density profiles of galaxies in these massive SZ-selected clusters. And firstly, we looked at the SPT selected galaxy clusters in the early 2019, where we had a sample of around 300 SZ-selected clusters. So one thing I should say is that optical selection gives you many more objects of the order of thousands, as opposed to these SZ-selected objects. So the error bars were much larger. So we were looking at a sample of 300 SZ-selected clusters, and the measurement are shown in this pink dashed line in the bottom panel. And the expectation from simulation should be close to this black shaded region. And we saw that for the SZ-selected clusters, actually, statistically, there was no difference in the expectation of the splashback radius from where we think it should be. There was no evidence for a shift of 20% that we were seeing in these optically selected clusters. So we've been following that up now. So more recently, we've also got a sample of advanced galaxy clusters from the Advanced ACT survey. So we take these ACT galaxy clusters, which is now a much larger sample of close to 1,000 objects between a redshift of 0.1 and 0.7. At an average redshift of around 0.44. But essentially, we have a sample of 1,000 really massive objects in the sky. So we take their locations and cross-correlate them with the DES galaxies that we see in the DES dark energy survey, and measure the density profile of number density profile of galaxies around these clusters. And right, and so using these clusters, we've now been able to measure quite precisely the splashback radius. And firstly, before you're distracted by the colors, I can maybe draw your attention to the gray band, which is essentially the measurement for all galaxies, the distribution, the slope of the distribution of galaxies around a cluster, and it agrees quite well with the theoretical expectation, which is shown by this black line within error bars. Right, so so yeah, this is a good demonstration. So essentially what we measure is the number of galaxies going out from the center of the halo, and without splitting the galaxies in any way, this is the measurement that we get, and we measure this gray band as the slope of that density profile. And we see that for these SZ clusters, there's actually quite good agreement with theoretical expectations. Okay, so shifting gears a little bit. So apart from just measuring the location of this feature, which should essentially definitely be there, because if we believe in dark matter and if we believe that these dark matter halos dominate their environment, there should be a transition, a feature near the transition region of these objects. And I think currently we can say that we can detect it in data. Apart from that, the other thing is we have been looking at is how this feature plays out in the distribution of different types of objects that live in clusters, essentially. So one of the things that that I've been closely working on is basically looking at the distribution of galaxies of different colors inside these galaxy clusters. Galaxies of different colors are thought to have different star formation histories. In particular, blue galaxies are thought to be really star forming. They have very recent star formation, bursts of star formation happening now, whereas red galaxies tend to be old and red and dead with little or no star formation. So one of the things that has been known for a while in the field is this morphology density relation, in the sense that galaxies that live in clusters tend to be red, in the sense that tend to have very little star formation, little or no star formation. And it is thought that, there are many different possible reasons why that could happen. One of the reasons is that when galaxies fall into the dense environments of clusters, the gas in the halo of the galaxy is essentially stripped due to various processes like harassment, land pressure stripping, etc. So you don't have fuel to form stars. And then there are other theories like age matching, which says that, oh, generally just around these really dense cluster peaks, galaxies just tend to be older because they have collapsed, their halos have collapsed earlier, and therefore they're red. But in any case, if galaxies are turning red primarily inside of a cluster, then we expect that the star formation should be sensitive to the orbits of the galaxies that live in these clusters. So that was our basic idea. So in general, you can see that there are many red galaxies in the cluster, but few blue galaxies and some green galaxies, right? And they have very different shapes. So, and what we also found is that the location of the minimum of red, blue, and green galaxies tend to be quite different. The red galaxies seem to have a very sharp splashback-like feature, whereas the green and blue galaxies have a weaker feature, and that appears to be shifted in an inner region. So one of the things that we realized while working on this is, of what could be happening, is that we could be looking at the actual dynamical evolution, the signatures of the dynamical orbits of these galaxies on their density profiles and the location of their minimums. So in the sense that we try to use the splashback radius as a clock inside the halo, in the sense that a population of galaxies that shows a splashback-like feature essentially must have reached its apocenter. So it gives you a time scale which is which is sort of uniform across different halos of about 2 gig-years, telling you how long the galaxies have been inside the halo. So if we think of a blue galaxy falling inside the dark matter halo, as time goes by, the blue galaxies change from blue. Their star formation rate, if it changes from blue to green to red, this is a simplistic toy model. Then if you track them in their phase space, they basically, their phase space streams cut out at different locations. So a blue galaxy that falls in, reaches pericenter, starts to lose its gas, and never really reaches maybe apocenter, and it's turned into a green or a red galaxy by the time it reaches apocenter. If this is the case, then the boundary between the multi-streaming region for the blue galaxies, which is 1 stream plus 2 stream, and the single stream region is at a smaller location than the expected splashback radius of those galaxies, apocenter. So we use this simple model, so that possibly can explain the shift in the location of the minimum, that the red galaxies actually, the galaxies that do make it out to the apocenter of their orbits or the splashback radius are the red galaxies, whereas the blue and green galaxies sort of change into different star formation properties by the time they reach apocenter. We use this simple quenching model. Firstly, we just doing a comparison with simulation, we sort of estimated the average times that the different populations of galaxies have probably been inside the clusters. So we found that the blue galaxies should have fallen in less than about 1.5 giga-years, whereas the red galaxies contain a population that have been inside for more than 3 giga-years or so. Then we fit a simple quenching model of how star formation evolves inside galaxy clusters with a simple delay time and a quenching model. So there's a short delay after which it starts to quench exponentially. And we try to constrain that model using actually not only the splashback radius, but the full profiles, because you have that information. And we found that, and we could constrain quite well the quenching time from these measured density profiles of different colored galaxies. Yeah, so it looks like there's a short delay time of about a giga-year before galaxies enter in this very exponential quenching phase with a shorter time scale. And that delay time is essentially quite consistent with the time a galaxy takes to reach its pericenter, after which it starts to really kill off most of its star formation. So that was some of the things that we've been thinking about. And apart from that, so using this, now that we have, a different, like an added perspective of what the structure of the halo is and what the features in the density profile is, and how we can map them to the dynamical phase space evolution of galaxies, we could try to use them in different ways to sort of infer properties of galaxy evolution from the distribution of the galaxies in the cluster. And finally, before I end, this is the most recent work that we've been doing. This is actually now published, not in prep. So we've also, with the 1000 act clusters, we can also actually measure weak lensing quite well. So we have quite good signal to noise in the weak lensing measurement. So we can directly measure the matter mass distribution of the halo, not infer it through its galaxy distribution. And we find that the galaxy distribution and which is shown in this gray curve, and the lensing distribution agree quite well with each other, which was quite surprising in some ways, because we had expected to see larger differences in the inner region, but statistically the galaxies seem to follow dark matter quite well, we are finding. And also the splashback radius agrees well. And I think this is one of the first works where we actually have seen that the location of the particle splashback and the galaxy splashback are quite consistent with each other. And also we have both the dark matter distribution and the galaxy distribution measured together in the same plot. So we find evidence for a splashback-like feature in the lensing profile, and also some evidence that the density in the inner regions of these clusters is looking slightly steeper than what you expect from theoretical expectations. Right, so I think currently we are mostly working on this massive cluster scales, but there's no reason to not look at smaller halos and try to find these, find this feature and see what we can, and use it in different ways to learn about maybe galaxy evolution, gravity, etc. from it. And right, so some things that we've been working on is to look at smaller objects, particularly group-sized objects, where we still hope to get significant detection. And other than that, we're also trying to see how the feature in the galaxies and the dark matter link to the distribution of gas inside of these objects. Yeah, so I think I'm at the hour, and I'll leave sort of the summary slide up, and I'll thank you, and thank you for the opportunity for giving me, for letting me talk about my work. Thank you.
Thank you very much, Susmita, for this talk. Do we have any questions? We have a question from Vasilis.
Hi, Susmita. It's an excellent talk, actually. Slightly too dense for me. Anyway.
Thank you. I realize I might have put in.
No, it's okay. It's just it's a difficult day. I was a bit perplexed. I knew I was following way back the work that you probably already know about shell galaxies and how these were created, and it's very similar, the problem, right?
Yeah.
With the original simulations that Peter Quinn was doing nearly 30 years ago, but even now, Hernquist and his group with Illustris, they have identified those, right?
Yeah.
And I presume the logic is similar in your work, right? That you basically dynamical friction forces this material to escape, right? And typically those, in order to see the shells, either in dark matter or in stars, most of the interaction needs to be in minimal angular momentum, in nearly Bondi accretion, in order for them to appear more visible, right? So rather than sort of like, going around. Yeah. However, in the case of galaxies, the amount of material that was coalescing in these caustics that you call, right, was not much, right? Yeah. And actually, in order to be able to detect it, Malin and Carter were doing all these fancy techniques, unsharp masking and all those things to actually make them visible. So I couldn't really follow the details, but you argued that you can actually measure the actual mass, the dark matter mass in the shell. Will be the one that would produce the lensing or not? In a sense, how will you see the mass, right?
Yeah, it is very hard to actually associate a caustic. Yeah, there is very little dark matter mass in the caustics as well. So we are not actually measuring the caustics. What we are measuring is just the transition from the infall region, right? So the caustic basically makes a boundary. The outermost caustic makes a boundary where you have things which are orbiting inside of it and things that are not orbiting inside of it, outside of it, right? So you are just measuring that transition, essentially. So you're just coming from a region where you have only one stream, right? Things which only have a negative velocity.
And what is the observable?
Yeah, so the observable is the overall density of dark matter, right? So maybe I should just clarify that. Right. So the observable is essentially just number of galaxies as a function of radius, right? And what you're measuring is a difference in this shape and this shape. So there's a transition at the location of the caustic. Inside of this caustic, you have things which are orbiting, and outside of this caustic, you basically have things that are just falling in, and you're essentially measuring this sort of smooth transition. So it's very hard to actually associate what we measure to a caustic. We
right.
know,
I mean, how do you know that there is a caustic there? Because it may very well be that there is no caustic. I mean, a very small fraction of the galaxies are shell galaxies just because of the, of the dynamics, right? I can imagine that in the case of dark matter, just because of the fact that we assume that it's collisionless, so it will not depend on the sort of like details, gas ratio, gas and star ratio. So you will have it, right? But effectively, so you don't observe the caustics themselves.
No, we don't observe the caustic.
Okay.
It's just that or at least we have not been able to associate it with the caustic. We observe the jump that happens in the overall density when you jump the caustic. But to associate it with like the topographical feature or whatever a caustic is difficult. But we do see that sort of the red galaxies become really, really steep, for example. So one of the things that could be happening is that the red galaxies essentially, actually, the things that reach furthest out in the halo are things that have very radial, low angular momentum orbits. And they are the ones that reach the furthest out and are most likely to be associated with the caustic shell. So there we actually start to see a sharp feature. But yeah, I think it'll be some work before we actually, it's very hard to do it in galaxies for sure. But yeah, it's going to be difficult to find. I was actually just thinking about shell galaxies. So the galaxies are happening on a much smaller scale. So it's like when the galaxies are merging and the stars are, it's the galaxy's potential. But this is on a larger, like the full dark matter halo scale. Yeah, in the starlight we can see the caustics, but in galaxies you have to.
We have a question from Yorgos in the chat. He says, great talk, Susmita, thank you. What about splashback and cosmology?
Yeah, people have started thinking about this now, particularly because it's a fixed scale of the, it's a fixed radial scale in units of R over R200M. So it is sensitive to the, and it's sensitive to what redshift your cluster is in. So people have thought to use it as a measure of sort of Hubble constant or a fixed, a distance, a standard ruler. And there are some work that is starting with that. There is some work that is starting with that now. Yeah, I mean, it's interesting, but these clusters, so there's some work on splashback and cosmology. There are a lot of challenges, like modeling the clusters are quite difficult in the sense that modeling their actual mass distribution can be quite sensitive to your selection procedure, etc. So I think there's a long way to go before we actually measure Hubble constant using splashback and convince people. But yeah, in principle, some people are definitely thinking about it, like Eduardo Roso's group, etc.
Any other questions? Tanyo has a question. Tanyo?
Hi there. Hi, Susmita. Very, very nice talk. Thank you very much. I had a question from an observer point of view. When you showed the results in the density profiles from I think there was the DESI survey and also from weak lensing, right?
Yes.
And you were comparing them with the models and showing that that there is this shift of about 20%.
Yeah.
Between the actual data and the models. Actually, I was taking a look at the data itself, not the models. And do you believe that there is a difference between the density profiles that come from galaxies and those that come from lensing? Because wouldn't that mean that somehow galaxies don't follow the profile of the dark matter subhalos that they should be living in? Or I don't know, or maybe it's a simplistic.
So, just to no. I mean, so there's actually I just want to clarify because there might be two questions. So so are you asking if we expect
why
the lensing and the galaxy to match, or
yeah, they should? I would expect that they would match, right? If the galaxies live in dark matter halos. So I don't understand why they are different.
Yeah, so right, so I think we do find that so you have we do find that the galaxies do follow we actually are finding that the galaxies and the weak lensing measurement are quite consistent with each other. So on the top panel is the galaxy and the bottom panel is the weak lensing. So they generally agree with each other, and that is what we found.
Okay.
So this offset is when we compare the galaxies in observations to the subhalos in simulations, essentially.
Okay.
So yeah, so the subhalos splashback radius should be similar to the overall full dark matter host halos splashback radius. So we don't find in red matter clusters we were finding this shift, and yeah, the galaxy should follow the subhalo. So it was confusing why we didn't find.
No, I wasn't sorry. I was interpreting that that the data from lensing and the data from galaxies, the deep is at slightly different position.
Okay.
That maybe is within the uncertainties, but I don't know what those uncertainties are. And if you have those uncertainties in the data, I wonder if that 20% difference with models is significant or not.
I see. Yeah, I think we would be very surprised if the dark matter galaxies do not follow the So yeah, I think with better data we should be able to shrink these error bars quite a bit. They do cut. So there's one reason why galaxies could have a slightly smaller splashback radius, because galaxies, sort of unlike the dark matter particles, which make up this feature, the lensing, dark galaxies, if experience dynamical friction, as I was saying, like they will slow down sometimes if they're really massive. So that sometimes pushes it to a smaller radius. But we haven't actually seen like statistically significant evidence for that yet. We're mostly statistically they seem to agree, but yeah, I mean it'll be interesting to see what happens as these error bars shrink. Yeah.
Okay, thank you.
Sure.
Other questions? Okay, since I don't see any activity now, I can hijack the conversation. So I have a question on this one also. So you said that you think the discrepancy is because of selection effects in the clusters and the fact that the masses of the clusters are not measured very well, right?
Yeah.
So where does the mass enter here? Because I don't think that, I don't see you having rescaled the radius and you're just stacking everything together, right? From all galaxies, basically. Are you assuming perhaps some cutoff in cluster mass, in simulations and observations, and you want these to be the same? So how does mass and cluster selection enter and could affect this measurement?
Right, yeah. So in the observations, we find, so these observations are averages over sort of 8,000 clusters, right? And those 8,000 clusters are not randomly selected. We select them in a mass regime, and the mass we infer is from this observable richness, which is basically counting up the sort of number of galaxies that you have in that dense region. So so you measure richness, and then you have some calibrated mass richness relation. Right. So we have a distribution of masses for our stacked sample, right, in the observation. And when we take that distribution of masses and select the exact distribution of masses from the simulations, we get these green curves basically and this black curve.
Okay. So
yeah,
what
so we try to make the same mass selection.
Okay.
And there we see a difference. Yeah.
So what kind of mass range are you looking at here?
Yeah, so these clusters are sort of above 10 to the 14. So this is lambda, so richness greater than 20 clusters. So so it's everything above 10 to the 14. But yeah, so but like the mass function falls up quite steeply. So most of them are within like 1 to 10 to the 14.
Okay.
Yeah.
And then the other question is, I guess you're looking at it now, but why are you not using clusters with X-ray measurements of mass?
Yeah, there's no reason not to.
Okay.
I think okay, so one thing is we need the, right, so because the best signal noise measurements come from these, numbered like galaxy distributions rather than the weekend. So we need it to be in a well-characterized galaxy survey field. So which is why we use, so there's an overlap between like DES and SZ surveys, dark energy survey and SZ surveys. But yeah, I mean, someone has definitely looked at the MCXC clusters. We should definitely look at, there's no reason not to look at X-ray clusters.
So basically you just need your selection criteria to be well characterized to match this with simulation.
Yeah. That is really important, at least to understand what's going on. Yeah.
Okay, one more question. You said that in early results, you saw no dependence with redshift of the location of the feature, while you expected one, right? Do I remember correctly?
Yeah.
Simulations, you expected one. How about newer results? Does this persist? Have you looked at it as a function of redshift?
So I think there's two issues. Probably this is a little misleading. So the expected shift from the redshift evolution is in this range is not very dramatically large. So there should be some shift where we didn't see it, but it's not that large. Currently, we have looked at the redshift evolution in ACT clusters. There is a difference, but it's a little, there's some complication because the redshift shift that we see in simulations is when we look at clusters which also have very similar accretion rates. So it was binned in accretion rate and redshift. So that is a bit hard to do in data because it's hard to select, fast and old clusters, which is actually something doable with X-ray. But yeah, but currently the short answer is that we do see, at least by breaking the ACT clusters, which is a much smaller sample, some shift with redshift for now. Yeah.
Okay. Thank you. Any other questions? Okay. Since there aren't any other questions, let me thank you once more very, very much for this wonderful talk. It was really nice to have you here, and we'll catch up some more. Thank you very, very much. Thank you, everybody, for joining.
Thank you very much.